Imagine two identical bottles sitting on a laboratory bench. One contains hydrochloric acid, the other contains sodium hydroxide. Neither bottle tells you what is inside. No labels, no warnings, just two clear, colorless liquids. Now I ask you a simple question. How would you know which one is the acid and which one is the base? Would you taste them? Absolutely not. Would you smell them? Definitely not. Would you look at their color? That won't help either. For centuries, chemists faced the same challenge. They could observe that some substances reacted vigorously, changed the color of indicators, neutralized one another, and formed salts, but they still needed a scientific explanation for why these substances behave differently. Then in 1887, one scientist offered the first widely accepted answer. His name was Svante Arrhenius. His theory became the foundation of modern acid-based chemistry and transformed how chemistry was taught across the world. But was his explanation complete, or did it leave unanswered questions? Stay with me, because by the end of this lesson, you understand not only what Arrhenius theory says, but also why scientists eventually need to go beyond it. Welcome back to this particular channel where chemistry is made easy, where difficult concepts become simple, logical, and unforgettable. Whether you are preparing for WAEC, NECO, JAMB, IJMB, JUPEB, GC, or you are studying chemistry at university, today's lesson is one of the most important topics you ever learn. Today, we are exploring Arrhenius theory of acid and bases, the first major scientific explanation of why acid and bases behave the way they do in water. Let's begin. Who was Svante Arrhenius? Every great scientist theory begins with someone asking a thoughtful question. Svante Arrhenius was a Swedish scientist who carefully studied solutions and noticed something remarkable. Whenever substances like hydrochloric acid dissolve in water, they produce particles responsible for acidic behavior. Likewise, substances such as sodium hydroxide release particles responsible for alkaline behavior. This observation led Arrhenius to develop a theory that was remarkably simple and practical. Instead of describing acid by their taste or corrosive nature, he defined them by what they produce in water. This marked the turning point in chemistry, moving the subject from observation to explanation. The Arrhenius theory can be summarized in two clear definitions. First, an Arrhenius acid is a substance that dissolves in water and increases the concentration of hydrogen ions. More accurately, because free hydrogen ions do not exist independently in water, they combine with the water molecules to form hydroxonium ion, that's H3O. So when you hear someone say that Arrhenius acid releases hydrogen ion H+, remember that those protons quickly associate with water to form hydronium ion or hydrozonium ion H3O+. Second, an Arrhenius base is a substance that dissolves in water and increases the concentration of hydroxide ion OH-. Notice something important. Both definitions depends on one condition: water must be present. Without water, the Arrhenius theory cannot be applied. That single condition is both its greatest strength and its greatest weakness. Let's see how it works. Imagine adding hydrogen chloride gas, HCl, into water, H2O. The moment it dissolves, the HCl bond breaks. Hydrogen is transferred to water, producing hydrozonium ion, while chlorine remains as chloride ions. The reaction is HCl equals to H3O+ to HCl- equals. Those hydronium ions give the solution its acidic properties, and they are responsible for many familiar characteristics of acids, such as changing the color of indicators and reacting with certain metal and carbonates. According to Arrhenius, because hydrochloric acid increases the concentration of hydrozonium ion in water, it is classified as acid. Looking at sodium hydroxide here, when sodium hydroxide dissolves in water, it separates into sodium ion and hydroxide ion. The equation is NaOH equals to Na equals plus OH- equals this. Those hydroxide ions are responsible for the alkaline properties of the solution. They make the solution feel slippery, turn red litmus paper blue, and neutralize acid. According to Arrhenius, any substance that releases hydroxide ions in water is classified as base. Again, notice that water is essential. At this point, you might be wondering why Arrhenius placed so much emphasis on water. The answer lies in observation. Many of the acid-base reactions studied during his time occurred in aqueous solutions. Water was the common medium in which acid and bases dissolved ionized and reacted. His theory successfully explained countless reactions in laboratories and industries. For many years, it was exactly what chemists needed, but science never stopped asking questions. Now imagine a completely different experiment. There is no water anywhere, no solution, no solvent, only two gases, ammonia gas and hydrogen chloride gas. When they come together or come in contact, they react immediately to form a white solid known as ammonium chloride. The reaction is Na3 gas, HCl gas to give solid of Na4Cl. Look carefully, where is the water? There isn't any. Yet acid-base reaction has clearly taken place. According to Arrhenius theory, this reaction should not even qualify because its definition depends entirely on aqueous solution. This was a major challenge. Scientists realized that although Arrhenius theory was valuable, it could not explain every acid-base reaction. Chemistry needed a broader theory. This scientific challenge eventually led to the development of Brønsted-Lowry theory, which explained acid-base reactions in terms of proton transfer, whether water is present or not. Later, the Lewis theory expanded the concept even further by focusing on electron pair transfer. Does this mean that Arrhenius theory is wrong? Not at all. It means one of the most important theories in chemistry. Whenever you are dealing with aqueous solutions, especially at secondary school level, it provides a clear, practical, and reliable framework. It is also the foundation upon which more advanced acid-based theory were built. Scientific progress rarely discards earlier ideas completely. Instead, it builds upon them. If you are preparing for examinations, pay close attention. This question appears regularly. According to Arrhenius theory, an acid is, the answer there is a substance that increases the concentration of H3O plus or H plus in water. Question 2. According to Arrhenius theory, a base is a substance that increases concentration of hydroxide ion in water. Question 3. Which condition must always be satisfied before applying the Arrhenius theory? A reaction must occur in water, or you say an aqueous solution. Remember this simple phrase: Arrhenius equal to water. If there is no water, think carefully before applying Arrhenius definition. The Arrhenius theory helps explain many everyday processes. It underpins the chemistry of cleaning agents, laboratory neutralization experiments, water treatment, food processing, industrial manufacturing, and many analytical techniques used in schools and research laboratories. Whenever acids and bases are dissolved in water, the Arrhenius concept provides a straightforward explanation of their behavior. Now it's your turn. Answer these questions in the comments. Give one example of an Arrhenius acid. Number 2, give one example of an Arrhenius base. 3, why is water essential in Arrhenius theory? 4, can the Arrhenius theory explain the reaction between Na3 gas and HCl gas? Explain your answer. I will be reading your responses and I'd love to see how well you've understood today's lesson. Today we've traveled back to the origins of modern acid-based chemistry. We've learned that the Arrhenius theory introduced the first widely accepted scientific definitions of acid and bases based on what happened when the substance dissolved in water. We've seen that Arrhenius acid increases the concentration of hydronium ions, while Arrhenius base increases the concentration of hydroxide ion. We've also discovered the theory's greatest limitation, as it's only applied to aqueous solution. The limitation did not diminish its importance. Note that instead, it inspired scientists to develop a broader theory that expanded our understanding of chemical behavior. In our next lesson, we look at Brønsted-Lowry, how it solved the puzzle of acid-base reaction occurring without water, opening the door to a deeper understanding chemistry. If this lesson has helped you understand the Arrhenius theory more clearly, please support this channel, this platform, by giving the video a follow-up or thumbs up, by sharing it with any other person, subscribing, and so that you won't miss any other chemistry class. Let's continue making chemistry simple, practical, and enjoyable for every learner. My name is Omotola Fayomi. More cheers.